Pythagoras' theorem in 3 dimensions. Here I've created a model to explain what I mean by this. We have a cuboid. The diagonal from the top corner to the bottom corner at the opposite side, PQ, is coloured in red. We'll call it length A. If I imagine taking a journey from P to Q going along the edges, we might travel along B and then C and then D, as in the diagram. You could think of this as taking a right angular journey from P to Q. At each vertex, I'm turning a right angle before I travel on the next edge. The rule by Pythagoras says that a squared is equal to b squared plus c squared plus d squared. Let's apply this to a question. We're given a diagram. It shows two walls, one of length 10 meters and one of 5 meters, meeting at right angles. Although it doesn't look like there are right angles in the picture. So let me just show you where I mean the right angles here. This angle in between is at 90 degrees. Now it might be easier to imagine this if I complete a cuboid. Imagine that this is part of a cuboid. So I'm drawing some extra lines that are not in the picture. But we could think of this, the journey AB that we're being asked to find is, like in the previous image, is the diagonal of a cuboid. And we want to calculate this distance. So if I could get a right angular route going along the edges, so I'm going to label some points here, C and D, to get from B to A, well then I could use Pythagoras' theorem in 3 dimensions. So I could travel along BC, then C to D, and D to A. And this would be a right angular route. So Pythagoras' theorem in 3 dimensions says x squared should be equal to 4 squared plus 10 squared plus 5 squared. And this is our solution. So x is the square root of this, which is the square root of 141. And that's equal to 11.9 when we round it off to 1 decimal place. This example demonstrates how understanding how Pythagoras' theorem works in 3 dimensions can really simplify what otherwise would be a very complex question.